Hi, welcome to another installment of Chemistry Cheat Codes, a series where you get to hear advice from a lab TA on Chem Lab success. Today's installment is episode 3, the Rocket Lab. If you attend a certain university, your third experiment in general chemistry lab may very well be your favorite lab of the year, or it may very well be your undoing and your mortal enemy. I'm just joking, of course. Your mortal enemy is yet to come, believe me. The Rocket Lab has a very simple objective. Synthesize rocket fuel, deposit it into a plastic shuttle, and ignite it to propel the shuttle as far as you can. Okay, maybe that didn't exactly sound simple, but remember, we let college freshmen do this, so how bad can it really be? I hope you are starting to sense a pattern here in these videos when I tell you that we are not exactly testing your prowess as a rocket scientist here. Let's go back to the three main themes of chemistry lab: experimental design and error analysis, critical thinking, and finally execution of technique. You may be either excited or frightened when I tell you that this lab hits on all three. However, none is more important in this lab than experimental design and error analysis. What most students find frustrating about chemistry is that they attempt to learn it by memorization and regurgitation. This is an unnatural and ineffective way to go about learning anything except maybe a few choice subjects such as anatomy. It is better to understand the core principles at work and be able to apply these patterns to any given problem. This kind of thinking is tackled by this lab by giving you a fairly open-ended procedure and a specific goal to meet. Some of you might get lucky and launch your pipette on the first try. If this happens, then good for you. For the rest of you that fail on your first try, also good for you, because it's time to develop critical thinking skills and experimental design skills. Critical thinking is not memorization and regurgitation. This is simplistic thinking. This kind of thinking is not developed in lab, as simplistic thinking is not really a useful skill. Critical thinking involves synthesis. You take two or more ideas and morph them together to get a new original thought. An original thought in this definition doesn't entail that nobody has ever had that thought before. It just means that that thought is new to you. We start the critical thinking process usually by asking why. When your bulb fizzles out, there could be a multitude of reasons for why that happened. A critical thinker first needs ideas to work with. So come up with ideas on why the bulb didn't ignite. Try and figure this one out on your own, but if you're completely out of ideas, consult your TA. Look at your ideas that you have identified. By the way, this is the most important part of the critical thinking process, and assign a chemical reason to every single idea you have. Let me quickly explain what a chemical reason is. I use the term chemical reasoning to describe a thought process that has a logical basis in chemistry theory. For example, a chemical reason for sodium being less reactive than potassium is that potassium has less ability to pull its valence electron towards itself. Thus, it is more able to participate in a chemical reaction. An example of what is not a chemical reason is saying that potassium is more reactive than sodium because potassium is less electronegative. Yes, I know that they mean the same thing, but all too often I get students who prefer to just memorize trends instead of understanding fundamentally what's occurring, and they end up getting lost when they write their post-lab. Okay. Back to the critical thinking process. If you cannot assign a chemical reason to something, this would be a good time to ask your TA for help, or you could ask your classmates to help you identify the chemical reason. If you find that there is no chemical reason, in my opinion, it's best just to cross that one off. Now we start talking about experimental design. You need to synthesize a remedy for the reason why your bulb didn't ignite, and then execute that remedy. The synthesis of ideas here, that is the critical thought, involves you taking the idea that is the problem and the chemical reason and morphing them together to mitigate. One by one, test your remedies until you find the culprit and your bulb ignites. Remember that you should really only test one at a time to be true to the scientific method. Record detailed observations and details about your procedure itself for use later if you're still having trouble. This is error analysis at the same time. If you find your bulb still doesn't ignite, well, I'm sorry to have to say, go back and do it again. Now a quick note about execution of technique. This is the first lab where you are expected to execute a moderately difficult technique, and we understand that. You are not on your own with this, and truth be told, it is very likely that some of your failed launches will be due to you not having properly deposited the fuel and oxygen into the pipette, and that's okay. This can be included in your list of ideas of why the pipette didn't launch, but try to be specific about which aspect of the technique was not executed properly. You also do not need to assign a chemical reason to this, but you should try to assign a reason nonetheless and use critical thinking to mitigate it just the same. This is a very fun lab and an exciting one when you finally launch a bulb. Personally, this is one of my favorite labs to do both as a student and a TA. Thank you for tuning in to another installment of Chemistry Cheat Codes. I hope to see you next time for episode 4. This extra credit scene is just supposed to serve as a little more clarification on what I mean when I say chemical reasoning. To further this point, let's say that you're doing this lab and your bulb didn't ignite. Sorry about it. You identify a reason, that is that the gases in the pipette bulb weren't mixed properly. Now that's all well and good, but what is the chemical reason? The chemical reason would be that if the gases weren't mixed well, then the molecules wouldn't be able to come together often enough to react well. Why chemical reasoning is so important in critical thinking in Chem Lab is that it allows us a tool to be able to see more clearly what is going wrong in the experiment and how to effectively mitigate. In this example, since we identified poor mixing of gases as the problem, then thought about why poor mixing might affect the launch on the molecular level, and concluded that it would by hindering the molecules from coming together to react, we can move forward to mitigate with reasonable confidence that fixing the mixing problem will have a good chance of creating a successful launch. Doing this, rather than just trying anything that might sound good and using a guess and check methodology, is far more efficient. More importantly, however, knowing the chemical reason makes us better chemists and engineers, as we can use this thought process to solve countless other problems thrown at us in both chemistry and other disciplines of science and engineering.